Okay, so hello everyone. I'm from Unity, and I wanted to give a talk today on using Unity to generate training data for machine learning and why that's a cool thing to do. Although I'm realizing at this point that the subtitle might not be necessary. It seems like everybody kind of is on board with it being a cool thing to do. Nate actually gave me a great setup. The several slides he spent explaining how there isn't enough data available for him to do training without taking a bunch and manually labeling it is a great point, and we'll reference back to that later. But rough agenda: I'll tell you who I am, what I'm talking about, why I'm talking about it, and how you could talk about it in the future too if you want to. And then we'll go to a Q&A. And just a little disclosure: some of this might be a little bit high level. I wasn't sure exactly how many people were going to reach in the stream, so I made sure to clarify a lot of terms in here in the beginning. So we'll start with who am I, what is machine learning, and why you should care. So hi, I'm Devin. I work on the perception team at Unity, and the perception team is this interdisciplinary group of machine learning researchers, software development engineers, many people kind of that fit in between those two titles. And we kind of share this common goal of what we call democratizing machine learning, and that is simply to say that we would like machine learning and machine learning training to be more available to basically anyone instead of only available to those who have access to scores and scores of expensive data that you need normally for a machine learning model. And so I'll clarify these terms a little bit, because I know that we say machine learning a lot, but what we really mean, or what I'm really talking about here, is neural networks. This talk can apply somewhat more broadly to other types of machine learning, but I'm going to use these terms pretty much interchangeably. And then when I talk about perception, I'm not necessarily talking about computer vision, although I mostly am. Perception can also include a couple other things, and our team works in more than just explicitly computer vision. But at the same time, for the purposes of this talk, computer vision is basically the same thing as perception. And it's important to note that while computer vision is not necessarily machine learning in and of itself, you can certainly write a computer vision algorithm. It doesn't do any sort of learning. What I'm talking about here is this is the good stuff. This is what I consider the intersection of perception and machine learning, where the most interesting stuff happens, according to me, the person that works on these things. Okay, so why is this interesting? Well, I think I don't need to convince people very much of this, but I wrote this stuff down anyway. So vision-based machine learning, it's super useful. There's a lot of interesting things you can do with it. I think it doesn't take much imagination to kind of see how it's already being applied, or to see how it would be valuable to improve machine learning models for their current applications. You might think of autonomous driving, assembly line automation, customer service automation. The more robust the models are, the kind of better these tasks, the more accurately these tasks get executed by whatever system is executing the model. In terms of customer service automation, maybe there's kind of a grocery identification application that you might think would be relevant. I made this point bigger. That's called foreshadowing. We'll talk about that later. Machine learning is also very difficult for kind of the same reasons. Nate, I'm glad you said it, so I didn't have to, but I'm going to say it again anyway. Machine learning neural networks can be kind of dumb, and that's because they are very sensitive to stuff that you have no idea that they would be sensitive to. And so cultivating your data set and making something that actually trains the algorithm to work the way you want it to is super important. And of note, I had a frowny face next to this very difficult point for most of today. And as I was going through it, I realized I should probably change this to a smiley face, because although it is sometimes frustrating that machine learning is so difficult, I think this is also what makes this such a cool and interesting field. So there are a lot of reasons why machine learning is hard. I'm going to focus on one very specific one, and that's just that it requires a lot of data, a lot of data. And that data is special, and it's unique to each task that you're trying to accomplish with whatever machine learning algorithm you've built. And it also is very expensive. And it's expensive because it needs to be labeled. And so if you want to teach a machine learning algorithm how to figure out what's going on in the image on the left, you need an image like what is on the right, where you have annotated the data in some way to describe to your algorithm what's going on in it. And annotations might not always look like colorful blobs. They might look like bounding boxes or a list of semantic clues about a scene or something like that. But ultimately, it really requires that someone sits down and goes through every single bit of data you want to feed to your algorithm when you're trading it and labeling it for you and labeling it accurately. And I think a point that's often missed is that if you want your model to perform really well, if you want it to be robust to most circumstances, it actually needs even more data. Give it some more, because the world is a complex and diverse place, and whatever data set you have is going to be biased, just simply due to the nature of how you collected it or where it came from. And edge cases, by definition, are not going to show up very often in that data because they're edge cases. But a lot of times, you need those edge cases. Maybe they're very important. The one that I always bring up is the baby stroller in the middle of the road. Autonomous cars should probably know how to identify that, but it's probably not a thing that's going to happen very often. So the question then is, how do we get all of this data? And traditionally, like we've described, you collect it from somewhere. You hopefully collect it ethically and with permission of the people you're collecting it from. And then you pay a group of humans to annotate it. And you really hope that is good enough for you, because gosh, golly darn it, that's hard to do again. It's very expensive the first time. It's just as expensive the second time and the third time you do it. So if you need more data, you're paying for it again. But what if we instead just generated that data? Enter synthetic data or sim data or data generated from simulation, simulated data, any of those. It's like real data, but it's fake somehow. And that's actually great because unlike real images, synthetic data can be made. There are a lot of examples of synthetic data. I've got a few here. You can see on the right, this is a picture of my cat hanging out in the entranceway to the Unity office in Bellevue. And it may occur to you that my cat cannot actually exist in 3 places at the same time. And he's actually never been to the Unity offices in Bellevue. This is a composite image that we've put together. And that means that even though it's composed of real parts, it's still a synthetic image. I thought this was a funny picture to share, but this is actually not the kind of data we'll talk about today. There's other types of data that they can be generated by AI. They can be a combination of real and digital parts. But what we're really talking about, the part that we're really interested in at Unity, because we have a fully featured rendering engine at our disposal, is fully synthetic data. That is to say, stuff that is just completely rendered. And so, what are the benefits of doing this besides the fact that you can make it whenever you want? Well, you have a complete guarantee that the ground truth for your data is completely accurate, as opposed to being human labeled like it often is. The ground truth is kind of implicitly defined by how you've generated your scene. Similarly, you have really precise control over how you generate your scene when you're generating your data. And that can be very important for capturing stuff like edge cases, or making sure that the trends and shapes in your data follow the pattern that you want it to follow. Maybe you've read a really cool paper about generalizing your neural network for a particular in a particular way, and it just simply requires that you expose it to lots and lots of data in a very particular format. And so you can do that, no problem with synthetic data. You define the rules by how the scene is constructed. And lastly, and I'm just going to restate it here, you can make as much of it as you want, and that's because it's generated by you, and it's not bound by the limitations of a finite timeline and a finite number of cameras existing in the world. So what are the downsides then? Obviously, there must be some, because conventional knowledge is kind of that we don't use synthetic data that much for machine learning. Well, downside number one is just that it's kind of mysterious. This handsome fellow on the right giving us the stank face may look very realistic to us. But some of the techniques that we use to generate rendered scenes in video games or otherwise are kind of shortcuts or cheats. And they're good for approximating how light behaves and how textures behave to a point that's convincing to the human eye. But is it convincing to a machine? Hard to say. It's a mystery. The other issue is just that it's you cannot just take a camera out into the real world and snap a couple photos, take it home, and label those photos. You need software to generate this data. But what's that you say? That's what I'm talking about right now? Well, yeah, it is actually. So maybe it's just that the downside of synthetic data is that it's kind of mysterious. So to sum up real quick, doing good machine learning is hard. And that's because you need a lot of very specific data. And sometimes you don't even know what data it is you need exactly, or what the shape of that data is, or what trends you need to represent in that data. Finding ethically sourced real data is expensive and time consuming, and comes with all sorts of human biases and is susceptible to human error during the labeling process, during the collection process, etc. Using synthetic data is cheaper and customizable, but it requires special software to be written. Well, luckily for you, we're writing that software, and it's called the perception package. So I didn't have a good segue for this slide. We made this perception package. It's a preview package. It's still kind of a prototype that we're working on, but we've released it. But in order to prove it to ourselves and to others that it can do something useful, we had to find an experiment. And so we did some stuff that other people did also, but we did it in Unity with our perception package. And so we focused on reproducing the experiment presented here by a team at Google Cloud AI. They created and trained a model entirely with synthetic data, just generated images of groceries and their associated ground truth. And then they evaluated that model and they pitted it against a model trained on real data, labeled data, manually labeled of also the same groceries. And what they found is that within a certain set of constraints, their synthetic data trained model actually outperformed the model trained on real data. And of course, this may seem totally shocking to a lot of us. And that is not to say that synthetic data wins, pack it in. But it is to say that under a certain set of constraints, for an experiment set up in a certain way, you can get pretty good results out of a model trained with synthetic data. And so we wanted to replicate this experiment. One of the key points of this experiment is that they started with assuming that photorealism isn't really necessary. And that's kind of freeing because that kind of goes against conventional wisdom and the expectation that all of our data needs to look as realistic as possible. What they found instead is that you just need to get kind of close enough to get the model to recognize the key characteristics of an item. And so the generator of synthetic data that they uses just simple lighting, shadows, added white noise and blur to simulate kind of the noise and blur that you would see on some camera capturing this imagery. They set up their scene with a kind of 3 layers. There's a background, the foreground, which is consists of all the detection targets that you want to train the model to detect, and then an occluding layer. And so the background and the occluding layer are just clutter. They're just stuff. They're there to generate noise, to confuse the model, to make sure that it's not just overfitting to a bunch of stuff floating in space. The occluding layer blocks the targets a little bit, but not too much, in order to further confuse the model. And then on top of that, they randomize the lighting and the hue of the clutter texture, so that you really just have kind of like a lot of noise happening around these objects that we want to detect. But then, because we want to train the model in a very structured way, they created this curriculum for the models, for the items that needed to be detected. And so they ran through in order a kind of list of scales from closest to the camera to farthest away from the camera, and poses to try and ensure that a good distribution of every single angle of each object was captured. And so we did that same thing in Unity, and we called it SynthDet. And these are some of the images that it created. And you can see they just kind of look like nonsense to a human eye almost. You can see that there's clutter in the foreground, and it's just kind of some squares and shapes and stuff. And the background is just also some more squares and shapes. And then you can see some very obvious detection targets, things that are the stuff that we want to train our detector to detect. And so we ran through a similar experiment with SynthDet, And we released this as well as an example project to kind of prove how that perception is useful, and that we could use it to train a model. And we got pretty decent results. And so we generated this grocery data and we trained it on a model. And sorry for my very thin lines, but I will just tell you that in the right image, the green boxes are pretty well aligned with the ground truth boxes shown in the left image, and the confidences are relatively high. Or most of them are the max that they can be. And so what we learned from that were kind of three key things. One, although synthetic data is great, we actually did kind of cheat a little bit on some of our better models. And it's not really cheating, it's science. We pre-trained with synthetic, but we used another round of training with real labeled images to kind of give it like a polished pass. And we found that while photorealism isn't necessary, it's still kind of necessary to make sure your simulated representation matches your real world representation. We actually had a very funny thing happen where the person who was creating the models in our sim was in a different region of the United States than the person who was capturing the real world labeled data for benchmark training and the validation pass. And so what we had was serial boxes that were almost exactly the same, but with slight design differences. Say there was a tag that says extra calcium in one place on one of the boxes, but in a different place in another box. And so even though they were effectively the same box, because there were these key differences, our results were significantly worse than when we noticed these differences and fixed them, and then we had a more accurate representation in sim. And the final one is simply just that intuition is great to have, and it's very necessary when you're training off of real world data, because you gain a lot from getting it right the first time. But when you have synthetic data, it's just as good to just do the experiment anyway. You have kind of an unlimited access to data of various forms, so just do the experiment. Do it over and over again. Do it as many times as you can, and see what works. And so you may notice that my numbers, this talk was a little bit number light. And that's because all of our numbers are located on our blog posts, and I don't have permission to repeat them here mostly. But and we also have some of them that are unreleased, and so we have an upcoming blog post that hasn't been released yet, and that has all of kind of like final numbers from these experiments. And so you can do this yourself. You can pull down a perception package from the package manager inside Unity. You can check out the SynthDet repository, and very soon you will get to see a blog post kind of describing in more detail our methodology and our results. Okay, and so that's all I got for you. Are there any questions?
Awesome. Great talk. Thank you, Devin. Let me just do a clap for you. And the audience is clapping too. Great. So I'm wondering if anybody from the audience has any questions. You're welcome to speak. The mics are on, so.
I have a quick question. I thought the talk was really great. I thought it was really interesting, unique take on the talk. I think my question comes with I think a worry would be that when we're using synthetic data, I think this is something you mentioned, that we might not be able to actually generate enough of the kind of small cases, like the stroller in the middle of the street, those little edge cases that we might not really see very typically in the data. Is there a concern that when we're generating synthetic data, we have an even greater chance of missing those really important edge cases?
Oh, I mean, absolutely. So I was being super reductive when I said that the only problem with synthetic data is that it's mysterious. But yeah, there's definitely kind of, I mean, it's all encapsulated in this idea that we just don't know what we don't know. And with real data, you kind of have this guarantee that it's going to look like real life, because it is. And so, yeah, there's definitely concern. And this is like the primary concern for, I think, a lot of people that I've talked to in this field, that sure, that looks right, but how do you prove that it's right? I know that if I take a picture outside that's representative, but I don't know that this simulated scene is also representative, especially representative in the ways that are important to some, you know, magical neural network with a bazillion steps and just a ton of, you know, operations that I don't, you know, I don't understand. I can't intuit what this thing is going to do. And so that, yeah, that is very much just like a super valid concern.
Thanks.
Cool. Any other questions from the group? Oh, I'm not. Sorry. Any other questions from the Zoom room? All right. Well, awesome talk. Super.